Break time now. Let me share two short but very interesting ones today. It is from Europe, America and so on. Maybe now even here we are having that. I asked my new girlfriend what sort of books she is interested in. What do you think? She said checkbooks, duly signed. Next one. The question is, what's the difference between a good lawyer and a great lawyer? Answer: a good lawyer knows the law. A great lawyer knows the judge. Okay, back to the course. We showed you a sketch a little while ago about the same thing. This is again the same thing but in a better colorful manner and so on. So here is the ingot, the original material, very uniform, right, and so forth. But here is the material which is entering the rolls, right? This is the roller, this is the roller, so the rolling mill. Here they are saying hot rolling, right? It could be cold rolling, hot rolling and so on. So these grains are large crystals. When they go through the roll, they become elongated, right? They become elongated. So that is why, because the diameter of the grains has decreased and the average grain dia is inversely proportional to yield strength. So if it was a cold working process, then this type of grain structure will generally remain, and therefore the strength of the material will have increased because of cold rolling. If it is hot rolling, these long grains are there, but once they are exposed to normal temperature and they start cooling, they break down into new grains, right? Nucleation and recrystallization starts to happen, and by this time the recrystallization has completed and the grains are still a smaller size. So it is not just that they are long, because they are now cooled. So you remember the annealing process and so on. When they are heated and cooled, then nucleation of new grains and recrystallization happens. But these recrystallized grains are still smaller in average diameter than the original ones. So the strength will be higher, right? Changes in the grain structure of metals during hot rolling. This is an effective method to reduce grain size and refine the microstructure in metals, resulting in improved strength and good ductility. In this process, cast structures of ingots or continuous castings are converted to a wrought structure. Wrought means which have been worked upon. This is English language. Wrought is the past tense of work. So they have been worked over during rolling. So this is a wrought structure, and that was the cast structure. So cast structure and now wrought structure. Okay. So it is not just that the thickness has been reduced, we have new sheets, or the shape has been changed and we have a new product, but also the strength of the material has improved during rolling. What are the basic types of rolling? Right, based on workpiece geometry. Flat rolling, shape rolling. Flat rolling is used to reduce the thickness of a rectangular cross section. Shape rolling, the square cross section is formed into a shape such as an I-beam or something. So this is based on geometry, either flat rolling or shape rolling. Based on the work temperature, of course, hot rolling, cold rolling, right? Any temperature above the recrystallization temperature, any temperature below the recrystallization temperature and so on, right? So hot rolling can achieve significant deformation because the material is softer, it is hot, so we can do a lot of deformation easily. Cold rolling produces sheet and plate stock. Usually we do not do a big thickness change in cold rolling. If we want to do it, then we do it in more than one steps. The starting stock, the original material is called stock, right? So a thick stock can be rolled into blooms, billets or slabs Blooms have a square or rectangular cross section. It is a name, technical name. Billets are usually smaller than a bloom and can have a square or circular cross section, and then they can be further rolled into structural shapes. Slabs are a rectangular solid with a width greater than twice the thickness and can be used to produce plates, sheets, or strips. So the starting stock material can be called a bloom, can be called a billet, can be called a slab, depending upon the original geometry. Here we are showing you the figures. This will be called a bloom, a square cross section. This will be called a slab, rectangular cross section. This will be called a billet. It is a square or rectangle but much longer in the other side. The billet shown here is a square, but the starting billet could also be round sometimes. And these blooms are used after rolling to have shapes like this I-beam or rails and so on. The slabs can be converted into plates or sheets or coils like your aluminum foils. And the billets could be changed into bars and rods and so on. Right? So sometimes you are just reducing the thickness, and sometimes you are changing the shape also. Here we are showing you further slabs, blooms, billets. These are the rolling mills, right? Triple rollers, this, that, different types, multiple rollers. And you can produce pipes, this, that. You can produce strips and thin plates. You can produce tubes and so on and so forth, right? So a starting material could be a slab, which is a thick plate, bloom, which is a thick square rod, a billet, which is a thin rod, and then you can generate different shapes. Now, the shapes generated are not too many. Only a few shapes are generally produced, but as I told you that I-beams and C-sections and so on are used in construction industries. So all construction industry all over the world, buildings, airports, bridges, all construction from huge workshops and buildings to simple, they all use these only few shapes. So these shapes may be a few that are produced by rolling, but the amount of material, of metals that is used up is huge, right? Hundreds of millions of tons and so on. Okay, so rolling is a major operation, even though the geometry that it produces are a few. Here we are showing you the same thing again, right? I am doing from different books and different places. Slabs, billets, blooms, hot strip, pickling, cold strip, welded pipe, scalp plate, steel plates, hot rolled bars, cold drawn bars, rods, wire and wire products, tubes and rounds, seamless pipe, structural shapes, right? I-beam, W-beam, H-beam, C-shape, rails, and so on. So you have a very good idea by looking at this just one slide that what are the major operations in rolling and what type of shapes they produce. Hot and cold rolling, of course, right? In hot rolling, temperature control is required for successful forming. Temperature of the material should be uniform everywhere. Rolling is terminated when the temperature falls to about 50 to 100 degrees above the recrystallization temperature, right? So it is seriously above, and it ensures the production of a uniform grain size. Cold rolling produces sheet, strip, bar and rod products with smooth surfaces and accurate dimensions. So this is just some general thing. Of course, right, that when it is hot rolling, there will be equipment needed, lot of heating equipment and so on, and there will be more safety concerns. But the material is softer, so with much smaller force, you can roll out into much larger capacity and so forth. So those type of things will always be there of hot and cold working of any kind, whether it is rolling or forging. Now to the mechanics of rolling, right? That part which becomes the basis of all calculations and so on. As I said in the beginning, in forging, especially in open die forging, we have a flat piece and we are just pressing it. The only thing is that are we taking a 3D slab or a 2D slab? Here it is a roll, right? The piece is going through a roller. So definitely you can't have a very simple geometry, right? So in the 3D shape, the roller is there, the roller is there. This is the material, and we are showing only one roller. There will be another roller on top, but it will be exactly symmetrical, so any one side will be okay. So this is the original material of width W0 and height H0. And it is being pushed into the rolls with an initial velocity of V0. When it is in touch with the rollers, its thickness is decreasing. So it is varying thickness along this length. This is not the length of the roller, this is the length of contact with the roll, right? This thing is coming, it starts touching here and finishes touching here. After that, there is no more thickness reduction, because now it has been reduced to this thickness, and this thickness will keep on coming out, right? So this L is not the roll length, it is the roll contact length, right? It is the roll contact length. And this capital R is the radius of the roll. So this is the initial velocity at which the material enters the roll. Now once it enters, there was some initial velocity and the rolls are also rolling. So at the end there will be a final velocity Vf, and this was the original width. Now there is a final width Wf. This was the original height, there is a final height Hf. And V roll is the velocity of the rolls themselves, right? So this is important that we understand this. This is not very complicated to see. And then if you see a 2D view of the same thing, then yes, this is the material before it enters the rolls. This is the material during the contact, and this is the material after the contact. So from here to here, you are in contact, right? And this contact angle is alpha. This contact angle from here to here is alpha. Vr is the velocity of the roller. V0 is the initial velocity at which the material enters. Vf is the exit velocity at which it leaves. And here you can see, right, V0, Vr, Vf and their relationship. And this is something which we will talk about later on. But something forward slip, right? Forward slip is the material easily going forward is Vf minus Vr upon Vr, right? Not V0. V0 is just there. But what is the final velocity at which it exists relative to the velocity of the roll? That difference upon original velocity of the rolls, this is known as forward slip, right? So this is just a terminology which we will use later on. Here I am just defining all the things which you already know. H0 initial thickness, Hf final thickness, delta H, H0 minus Hf is technically called draft in rolling. Vr, surface speed of roll, not the rotational speed in RPM, the surface speed. V0 is strip velocity at roll entrance. Vf is strip velocity at roll exit. W0 initial width of the strip. Wf final width of the strip. Capital R roll radius. L length of contact. So though you already know it, but I have summarized it here so that you know that all the different variables that are there in the equations or the derivations or whatever are here in one place. So now the same thing, slab method. We cut a slab, right? We cut a slab of the material. So this is at the entry zone when it is entering, and this is at the exit zone when it is exiting the roll. And we will define the same parameters and so on that we defined earlier. And once you apply the balancing equations, right, the conditions of homogeneous and so on, then you will find out the final stresses and contact stresses and pressures and so on.